All right, here we go. I'm going to present my solution to another free response question from a Physics 1 exam. This question has also been publicly released, so it's totally okay for me to be doing this. College Board will not be upset at me for doing so. In fact, they've given me permission to make these videos from their publicly released questions. So, as usual, I'll just remind you that I'm not really paying too much attention to the amount of time that I'm spending. I'm not trying to answer this as a student, but rather as a teacher trying to kind of walk you through it and hopefully explain the question and maybe some of the deeper insights as to just how to approach AP Physics questions, generally speaking. So with that said, let's get right to work. We're presented with a diagram that looks like a fairly standard situation. There is a rod, is what they identified in the question as, pivoted on the left end, and a small object described as a disk that's going to come kind of sliding in here to make impact with the rod. Let's just read it to make sure that we can pick out all of the really important bits here. So, let's see here. The left end of the rod of length d and rotational inertia I, we see those in the diagram, so, well, at least d is, so maybe I'll just kind of remind myself that the rotational inertia is described as I here, and that is specifically for the rod. It's attached to a frictionless horizontal surface by a frictionless pivot as shown. So fully idealized as far as we're usually concerned. Point C marks the center, which is to say the midpoint of the rod, and the rod is initially motionless but free to rotate about the pivot. The student's going to slide a disk of mass m disk, so let me just kind of highlight that there, towards the rod with a velocity v0, that's in the diagram, perpendicular to the rod, and the disk will stick to the rod. In fact, I'm just going to remind myself of this. It's going to stick to the rod, so that's really, really important because the outcome of this collision hinges on if it's going to bounce or stick to it, as we're going to discuss in detail soon. So it sticks to the rod a distance of x from the pivot point. So x just being that generic reference to how far it is from the pivot. The student wants the rod disk system to end up with as much angular speed as possible. Okay, so here's what's going to happen. That disk is going to come sliding in. It's going to impact the rod, which was stationary. It wasn't rotating. Upon impact, you can hopefully visualize quite nicely that with the disk sticking to the rod, certainly the two of them together will start to swing around that pivot point and rotate in the counterclockwise direction. This is best understood probably in terms of conservation of angular momentum, which does bring me to an important idea that I think a lot of people fail to really, really understand clearly. A lot of people assume that angular momentum is really uniquely true or uniquely a property of objects that are, quote, spinning. So if the rod is spinning around the pivot point, most people are totally okay with thinking that it does indeed have angular momentum, as it would. But a lot of people are thrown by this. This disk is just moving in a perfectly straight line before impact for sure. And yet, despite that, with respect to this pivot point, it very much does have angular momentum. So just to be clear about that, angular momentum doesn't require an object to be literally spinning. All that it requires is for an object, so this object here, to have a velocity that is at least in part tangent to a circle centered on that pivot. So if I can kind of just sketch that in here, imagine a big circle centered on the pivot. Something like that. Poorly drawn, I guess. But notice that velocity here that I've drawn in here has a component that is radially towards the pivot and a component that is not. In fact, this component is essentially tangent to that circle. So thanks to this component of velocity, that disk has an angular momentum about that pivot point even before it makes contact with the with that rod. Okay, with that said, let me just kind of clear all of that out. Get that out there. And yeah, press ahead into the actual first question here. So part A says, suppose the rod is much more massive than the disk. So to give the rod as much angular speed as possible, should the student make the disk hit the rod to the point, or to a point left of point C, at point C, or to the right of point C? So I guess we have the freedom of kind of moving this disk around kind of left or right before we imagine sending it in for that impact. So the question ultimately says, should we send it somewhere along here to make impact here, or should we instead send it to impact right at point C, or, as our third option, somewhere to the right of point C? Those are basically the three zones that we're considering. So, giving a moment's thought to angular momentum, it would certainly be true that the amount of angular momentum that this disk has is going to be maximized if that if that disk is located as far away from the pivot point as possible, especially considering that the velocity vector itself will be the same at each and every one of those points that we're considering. So by maximizing the distance from the pivot, it will have the maximum amount of angular momentum with respect to that pivot. Another way to think of it is that upon impact, there's going to be this interaction of the disk exerting force on the rod exerts force on the disk, and of course that can be thought of as the disk. Let's just focus on what's going to happen to the rod here. The disk is going to exert a force on the rod, disk exert force on the rod, which constitutes a torque, since that force of impact, in fact, let's just change color here for stressing this, that force that would be the result of that impact constitutes a torque, and the amount of torque does depend in part on the distance r that it's applied from the center, or really from the pivot point, I should clarify. So by maximizing r, we maximize that torque, and therefore will cause that rod to spin as quickly as possible. All right, so I think I'm ready to commit to my answer to that question. Just to return down below here, I'm going to say that we should be aiming to have this impact happen to the right of C. And as far as an explanation goes, we could describe this in terms of the angular momentum, but you know what? I think it'd probably just be easier to answer it in terms of torque. And doing so, I might write up something like this. The disk. The disk will exert a force. Onto the rod. Upon impact. The magnitude of the torque, or let's say of the torque, let's say, of this torque provided by the force depends in part on the distance it is exerted from the pivot. Okay. Larger distances produce larger torques. So the disk, just to conclude this, the disk should therefore hit the rod as far away from the pivot as possible, which is to say, to the right of point C. Okay. Actually, just to clarify, because we're talking about, maximizing the speed, and so far I've only talked about maximizing the torque. Let me just kind of string that together here so that I really am focused on the point that they're asking me about. This will result in the rod having the largest angular speed possible. Okay, that should do it. All right, moving on to part B. It says, on the internet, a student finds the following equation for the post-collision angular speed omega of the rod in this situation. And the equation that they've located on the internet is m of the disk times x, the distance that it impacted from the pivot, times v0, all of which is over I, the moment inertia of the rod. Now it says, regardless of whether this equation is correct or not, does it agree with your qualitative reasoning in part A? So in part A, I said we should, in order to maximize the omega, we should maximize the value for x, that distance that the impact will occur from the pivot. In other words, does this equation for omega have the expected dependence as reasoned in part A? So it's important when you're answering this question not to get distracted by all of the other variables, because we could analyze them whether the whole equation makes sense or not, and it may or may not. Let's not even waste our time being distracted by that. Let's focus only on what they're asking me to look into. They're asking me to look into whether or not this is consistent with my reasoning in the previous part, where I said we should maximize the value essentially of x. So considering that I see omega here equal to a bunch of variables, but I want to point out that x is in the numerator, which means that this equation is essentially suggesting that omega is proportional to x, which is to say that larger values of x, according to this equation, would result in larger values of omega. Well, so far as that is concerned, that is completely consistent with what we just talked about. So I'm going to check, yes it is, and I'll explain my reasoning as follows. The equation shows that the resulting angular speed, omega, is proportional to the distance that the disk hits the rod from the pivot. In other words, that value of x in the equation, which means that I'm just going to scroll down a little bit, which means that a larger angular speed is predicted for larger values of x as expected from part A, so it is consistent. All right, there we go. Trying to write quickly here. And so that should do it. Yeah, it should answer their question. X is proportional to, or so omega is proportional to x, completely consistent with what we said in part A. Moving on to part C. Another student deriving an equation for the post-collision angular speed omega for the rod makes a mistake and comes up with this equation. So we know that this equation is wrong. There's been a mistake made. So according to this equation, omega is equal to I x v0, all of which is over the mass of the disk to the fourth power. So without deriving the correct equation, so again, they're trying to downplay us from just going ahead and performing calculations. They're trying to really assess our deeper understanding of what's going on here, as well as our ability to just assess, like the plausibility of an equation without necessarily just chugging through the math to confirm or refute it. So without deriving an equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. And I want to stress physical sense here. I do recall a time when there's a bit of question about what that exactly means. I'm going to suggest that the stress here for physical sense would be trying to take us away from just the world of like pure mathematics. So for example, imagine somebody went in here and said, well, I'm going to perform a dimensional analysis of this. I'll just see what units would pop out, for example, from the right side of the equation, and if those units match the value for omega, I might say it's plausible. And if those units don't match, I might say that it's not plausible. So from a mathematical standpoint, there is some value to that. I mean, especially if it does not pass that dimensional analysis. If it doesn't pass the dimensional analysis, you could say it's definitely wrong. There's no way possible for it to be correct. So that would be meaningful, but is not what they're asking us to do. So don't do that if you're literally being asked to talk about physical sense. Physical sense is, yeah, you know what, these variables, I would expect, from a physical point of view that kind of checks out. So with that said, let's have a look at each of these variables. And considering that they're asking me to say, why does it not make physical sense? I think it's going to be enough to just find one issue with this. I can see at least two issues right off the bat here. I see definitely an issue with I being in the numerator, and I also have an issue with mass being in the denominator. So I'll just focus on the I being in the numerator, although either one would, I'm sure, be fine. Okay, so what is the issue with this equation? Well, how about if we say it's something like this? The equation does not make physical sense because, according to it, the resulting angular speed omega is, again, according to the equation, directly proportional to the rotational inertia of the rod I. Okay, so let's think about that. If the moment of inertia or rotational inertia of the rod was larger, so let's just go back to the diagram for a second. If the rod was made heavier, for example, or if it was made longer, for example, either one of those would increase the rotational inertia of the rod. Well, if you have this collision with the disc here, that enhanced rotational inertia of the rod would make it harder to rotate and would lead to a decrease in the angular speed of the rod after impact. So that's exactly the opposite of what this equation is predicting. It's saying, yes, if you make this an even more massive rod or a longer rod, the equation is saying that it's going to spin faster because of that, for the same impact, right, for the same disc collision. So that does not make physical sense here. So let me just kind of continue this. This was we're in part C now. So rotational inertia of the rod I. So let me just explain why that's a problem here. When in fact, let's see here, what am I going to say? A larger angular, or let's say a larger rotational inertia would lead to a smaller angular speed for any given, let's just say, for any given angular momentum. And I'll just explain why that is. Since angular momentum is the product of rotational inertia I and angular speed omega. So that should do. I mean, if you want to enhance your angular speed omega for any given angular momentum, if you want to even see, I could support that with the equation. I don't think really needed here, but just maybe I can show you and explain it. L is equal to I times omega, so omega is equal to L over I. So if you want to maximize the angular speed for any given amount of angular momentum L, you would in fact want to reduce the rotational inertia. Now, just for record, if I had only said this equation, what you see here, and not all of the supporting wording behind it, it really wouldn't have been an explanation. So I think that verbally I can support it with this equation, but I wouldn't leave it as this. Having this equation as part of my answer, I think, is completely fine. It's not going to cause any problems, but don't just throw math onto a question that is asking for an explanation, right? So if they ask you to explain, make sure that you're explaining by bringing up fundamental principles of physics and explaining how they pertain to the situation. So let's move on to part D. So for the remaining parts of the question, do not assume that the rod is much more massive than the disk. Okay, fine. I don't think that's really a super important part of this question, but sure. So question part D says, immediately before colliding with the rod, the disk's rotational inertia about the pivot is mass of the disk times x squared, and its angular momentum with respect to the pivot is given as that mass of the disk, v0x. Derive an equation for the post-collision angular speed, omega, of the rod. Express your answers in terms of the distance d, the mass of the disk, I, x, v0, and physical constants as appropriate. Okay, so they want an equation for the post-collision angular speed of the rod. So just to remind ourselves here, if I define my system to consist of both the rod and the disk, then they have to have a constant angular momentum throughout this investigation, as the disk is sliding along, for example, and then hits and sticks. So there's no external torques being provided just before to just after that collision. So they have to have a constant angular momentum. So before there is a rod which was not rotating at all, and then there's a disk that is sliding in, so it has angular momentum as discussed earlier. They collide and stick. They then will move as one single object. This is a situation that's really often seen in linear momentum, like if you just have two blocks colliding, moving along a straight line, for example. So in the translational momentum, that's often described as an inelastic collision. So this is effectively just a rotational equivalent of that. So let's get to work down here, basing it on the angular momentum conservation. So how about something like this? The angular momentum L, I'll just say final, has to be equal to the angular momentum L initial. So this is like just before the collision and just after the collision. So after the collision, L final, we're going to have we're going to have a moment of inertia I combined, let's just kind of write it in word form here, I combined, times the omega combined. That will have to equal to the I of the disk times the omega of, well, actually, hang on, they actually told this to me. Maybe I don't need to do that. They told me it's angular, yeah, right here. The angular momentum with respect to the pivot is given. So I'm just going to take advantage of that. The angular momentum is known to be m of the disk times v0x. And a friendly reminder that when they present us with value or letters to represent certain quantities, we have to use that exact same notation. Over here, I'm not going to be having I combined throughout this derivation, so I don't mind showing it here just kind of for clarity, but I'm going to soon be replacing that with the values that they really want me to have, or at least the symbols that they want me to use. Same thing with omega combined. All right, so what can I do here? I combined, that's going to be equal to the I of the rod plus I of the disk, like that, times the omega combined. In fact, I'm just going to say omega final, equal to basically the same on the right side, mass of the disk, v0x. Okay, now let's remind ourselves that the rotational inertia of the rod is given as I. So that's their notation. I'm going to start using it as of this moment. Plus the rotational inertia of the disk. They told that to me already here. It is m of the disk x squared, so I'm going to use that now using, again, their exact same notation. So m of the disk x squared. So that's the left side of the equation for the total moment of inertia, or rotational inertia. And they want me to find the equation for the post-collision angular speed. They're just referring to that as omega. So at this moment in time, I will start using that, omega, equal to the same, m of the disk v0x. Now, since they wanted this equation to be for the angular speed omega, I'm just going to solve this for omega by dividing that combined rotational inertia to the other side of the equation. Something like omega is equal to m disk v0x over I plus mass of disk x squared. And that should do it. That's exactly what they wanted me to find. In fact, let's just verify that by checking that I don't have anything in here that wasn't explicitly allowed for me for the sake of this question. They wanted to express my answer of omega in terms of, and of course, just saying in terms of does not mean that I necessarily have to have every one of these letters in it. It just means that I can't have anything that's not in this list. So they're allowing me to have a D. Let's see here. D, which is, hang on. D was given as, go back to the original diagram here. Oh, D is the full length of the rod. I don't really need to refer to D because they told me the rotational inertia of the rod is I. So, I could have calculated or derived an expression for I in terms of D and the mass of the rod if I have those special relationships memorized. Not needed here at all. So I'm not worried about the absence of D in my equation. So that's fine. The mass of the disk, I'm using that. I is good. That's the rod's rotational inertia. X, I'm good. V0, I'm good. So I am completely and totally good. There's nothing in here but the variables that I was told to use. So moving on, we're almost at the end here. I think this is the last part of the question. Consider the collision for which your equation in part D, the equation I just came up with, except now suppose the disk bounces backwards off of the rod instead of sticking to the rod. So up until now, we've been considering that inelastic collision where they collide and stick. Now they're saying, what if it bounces instead? Is the post-collision angular speed of the rod when the disk bounces greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks to it? All right, so going back to the diagram, sorry for all the scrolling here, but we're comparing two possibilities. So the original possibility was collide and stick. That's what we've been focused on up until now. We're now considering another possibility. In this new possibility, the disk is going to come in and it's going to bounce off of that rod. And of course, the question is, in which case will that rod be spinning faster? So thinking of angular momentum and reminding ourselves that it's a vector, if the disk comes and sticks to it, notice that the disk will still be moving in a counterclockwise direction around the pivot point after the collision. Again, if it sticks. But if it bounces, it would be going in the opposite direction. It would be going essentially in a clockwise direction around that pivot point. So in terms of angular momentum, as well as just linear velocity, the direction would reverse. And of course, that's a much greater change in angular momentum than a mere reduction in angular velocity. So because the disk is going to change angular momentum in a very dramatic way in a bounce, more so than if it had stuck, that means that the angular momentum essentially transferred to the rod is greater in the case of the bounce. All right, so if we go back down to that part of the question, I think I'm ready to answer it and explain it. So in which case will it be spinning quicker, or effectively will it be going with a greater, less than, or equal to the case if it had stuck to it? The answer is greater. Why is that the case? So again, we could write this up in probably more ways than one, but the way that I'm immediately thinking of it is in terms of that angular momentum transfer. If the disk bounces off of the rod, the direction of its angular momentum reverses from, I'm going to say counterclockwise, but I'll just abbreviate it as counterclockwise, CCW. That's a very widely accepted abbreviation. There'd be no doubt about it for anybody who's reading that. So it reverses from counterclockwise to clockwise. And so, what's the relevance of that? And so, it undergoes a greater change in angular momentum than if it sticks. All right. So if it sticks, so now why is any of this relevant? Because the change in angular momentum, there it is, momentum of the rod must be equal and opposite to that of the disk. In fact, let's explain, in order to conserve angular momentum in the system, the rod must end up with a greater counterclockwise angular momentum than in the previous case. Okay, so that should explain it and wrap up the question. I think that's completely it for this one. Good to go.